If you fell into the black hole at the center of the Milky Way, you would cross its edge without feeling a thing. No wall. No flash, not even a bump. The black hole is about 4 million times heavier than the Sun. Its horizon is millions of kilometers across, and still, at the exact moment you pass through it, the most famous boundary in physics is locally unremarkable. That is the first strange part. The second is that you would not be stretched into a noodle until much later. The third is that, once the stretching finally became noticeable, you would have less than a second left. So this is not the story of a dramatic line in space. It is the story of what happens when a line turns out to be a dead line. An event horizon is not a surface you crash into. It is the boundary beyond which every future path points inward, including every path light could take. From far away, that sounds like a wall. Up close, it is a rule about the future of space-time. For a non-rotating black hole, the tidal difference across a human body at the horizon is only about 1/10,000th of Earth gravity. For a 70-kilogram person, that works out to a force roughly comparable to the weight of a grain of sand. Your instruments would not announce, "Congratulations, you are inside." The horizon is globally the point of no return, but locally it does not have to announce itself. The word black hole hides a ridiculous range of sizes. A black hole made from 10 suns has a horizon radius of roughly 30 kilometers. Sagittarius. A star has a horizon radius of about 12 million kilometers. The larger one is more massive, but its edge is gentler because the mass is spread over a much larger scale. For the tidal gradient becomes destructive outside the horizon. You would be pulled lengthwise and squeezed sideways roughly 900 kilometers before you ever reach the edge. As Sagittarius, a bad opening. The tide prefix stification is a bad omen, not half in the wrong picture for the universe ends. Once you are inside Sagittarius' star, you have about half a minute of your own time left. Not half a minute before the universe ends. Half a minute before your path reaches the singularity predicted by the simplest version of general relativity. For a 10-sun black hole, the equivalent journey lasts only about 65 millionths of a second. The two black holes can differ by more than 500,000 in mass, and the clocks still give the same basic answer. The big one gives you a humanly noticeable fall, the small one does not. Then the calculation produces a more unsettling result. Ask how long remains after you feel a particular amount of tide. After 1 gravity of stretch, the remaining time is about due to 9 seconds. At 10 gravity, about due to 9 seconds. At a roughly tear-apart level, around due to 9 seconds. The mass changes where you die, not the short interval between the warning and the end. A supermassive one gives it inside. There is another famous black hole story. You fall through the horizon and watch the future of the universe race past overhead. That is not what a freely falling observer sees at the crossing. Light coming from directly above arrives at about half its original frequency. It is shifted down, not blasted blue. Look toward the rim of the black region, and some light is shifted upward instead. The black hole also takes up less of the sky than the pictures suggest. At the horizon, its dark region covers roughly 13% of your sky. The other 87% is still the outside universe, stars, dust, and light that have not been swallowed by your view. The scene is not a black curtain dropping over everything. It is a distorted sky with a dark patch in it, and you are falling through the patch. The infinite blue flash belongs to a different observer, someone trying to hover at the horizon by firing their engines forever. They do not cross. But the watcher isn't frozen permanently at the edge, glowing red for eternity. The fade is exponential, and its time scale depends on the black hole's mass. Around a 10-sun black hole, the characteristic fading time is roughly 1/4 of a millisecond. At Sagittarius, a star, it is about 11:07. It is close to 2 days. The final light has another surprise. It does not keep sliding toward infinitely red forever. Some of the last photons were emitted early, looped around the black hole's light ring, and leaked back out later. Their color shift saturates. What runs away is the brightness. There is a finite supply of photons reaching the observer. The image runs out of light. It does not become a permanent, infinitely faint photograph of you hanging at the edge. Nobody outside watches you freeze forever. They watch the signal fade until the last useful light is gone. Here is the piece of advice that sounds sensible, that see down a fall or a backs again. The usual freefall takes the longest. Argument compares paths that start and finish at the same two events. Inside a black hole, the singularity is not a destination event waiting at a place on a map. In the idealized picture, it is a surface in time. Different paths meet it at different places, so the familiar shortcut does not apply. If you cross the horizon already moving inward, firing your engines against that motion can extend the proper time you have left. The best strategy is not to keep burning forever. It is to cancel as much inward motion as you can, then coast. This is not a dramatic escape plan. It does not save you. It changes a very short clock by a very small amount. But the folklore has the direction wrong. Inside a black hole, struggling can buy time. The words center, centimerity sound like 20 ahead of you. Inside the horizon, that picture stops working. The word cannot ratting for argy. The mathematical version of the Severi. Its singularity theorems show that some paths become incomplete. The mathematical description ends. They do not, by themselves, give us a complete picture of infinite density or tell us what quantum gravity does at the end. Maybe the horizon is calm. Found this there on the fourth the stu forster for the court the source were the source the sort our first sort of the mar force or first server sus of the word versus the first of this or the poos port or the fusus that ones with the sus persons versions. So the quiet crossing is the answer from classical general relativity, not a final laboratory verdict. The horizon may be locally uneventful in the theory we know, while the deeper quantum question is still waiting for an answer. Put the pieces together. At a small black hole, you are torn apart before the edge. At a supermassive one, you cross whole. The horizon does not flash, the sky does not become the future on fast forward, and the outside observer does not keep a permanent picture of you hanging there. You get a quiet crossing, a distorted sky, a short clock, and then a point where the equations stop telling us what comes next. The event horizon was never a wall. It was a deadline written into the geometry of the universe, one you could pass without noticing, but could never pass back through.